Hey everyone, so this is lesson 9 of this trigonometric functions unit. And so we're going to look at average and instantaneous rate of change using these functions. I know we had just gone over average and instantaneous rate of change in the last unit, and it's going to operate in much the same fashion. So we're going to look at average rate of change first. We have this function here, which is relating how many weeks after the spring equinox to the temperature in degrees Fahrenheit. And we're asked, I guess there's no actual question specifically asking for us to check, but we're going to see what is the average rate of change from 20 to 40 weeks. So just as we did last time, average rate of change is the change in y and the change over the change in x for this interval. So from 20 to 40 weeks, and this is coming straight from the note. This is the graph that was in the note. From 20 to 40 weeks, what is our average rate of change? So our change in y, we're seeing how is our function value changing between these 2 points over the difference between these 2 points. So our x2 is 40, our x1 is 20. So what is f of 40 minus f of 20 over 40 minus 20? We look on our function, f of 20, that's right around 60 degrees Fahrenheit after 20 weeks past the spring equinox. That's going to be our f of 20. And our f of 40, that is 10. 10 minus 60 is 50, negative 50. 40 minus 20 is 20. So that's about negative 2.5. So what this means, every single one of these weeks on average, so in each of the weeks from week 20 to week 40, the temperature is falling by an average of 2.5 degrees Fahrenheit. We know the temperature is falling because the slope is negative. Our average rate of change for those 20 weeks, we're decreasing in temperature. We get a negative average rate of change, so our temperature is falling by that average of 2.5 degrees Fahrenheit every week. So average rate of change really is just a slope between two lines. Instantaneous rate of change. So we're going to look at what is the instantaneous rate of change at 20 weeks. We had mentioned there's two different ways that we can calculate instantaneous rate of change, depending on how accurate we want to be. We can find the difference quotient so that is we're finding f of our x value minus either just above or just below that value, and h h usually is going to be 0.01. Sometimes we might need a smaller number if we want more accuracy. Over the distance between x and x minus h, which is just h. So instantaneous rate of change, we're looking on this original curve. We want to find approximately what is the slope of our function at that exact moment. So this difference quotient, we're taking our value right at 20, we're taking a value just past on either side, and using that to estimate what the slope is at that point. So for this particular example, if we were to use the difference quotient, we would have f of 20 minus maybe f of, in the example they give 19.99, so we could do 20.01 over 20 minus 20.01, or 0.01. For our centered interval, the instantaneous rate of change, we're just going slightly above the value we're looking at and slightly below the value. And now our distance between these 2 points is going to be 2h. X plus h minus x minus h will give us 2h. This one requires a tiny bit more work because now we have to find f of 20.01 and f of 19.99. In this case, a little more decimals in those numbers, but it does give us a slightly more accurate answer. So if we were actually going to find this value, they give us that this equation for this example is 31 sine pi over 26 w plus 42. So if we're going to find the instantaneous rate of change at 20 weeks, we're looking for f of 20.01 minus f of 19.99 over 20.01 minus 19.99, or 2 times our h, so 2 times 0.01. We plug this into our equation t for finding t of 20.01, 31 sine pi over 26, 20.01 plus 42 minus t of 19.99, so 31 sine pi over 26, 19.99 plus 42, all in brackets, all of that over 0.02, 2h. Pull out our calculator. Again, make sure it's in radians mode. So we're going to do 31 sine of pi divided by 26 times 20.01 plus 42. 31 sine pi divided by 26, 20.01 plus 42. So t of 20.01 is about 62.52875001. Because we're dealing with numbers that are going to be so close to each other, it's good to use all of our decimals that we have available to us. Other function, t of 19.99. $62.584824.8247 all over 0.02. 62.52875001 minus 62.5848247 negative 0.0560746 over 0.02 is going to be negative 5.607. Oh, divided by 0.01, not 0.02. Should be half of that. Negative 2.804. That's what I get for trying to do it in my head. This equals negative 2.804. So, therefore, at exactly 20 weeks after the equinox, spring equinox, yes. The temperature is falling because our instantaneous rate of change was negative. Our temperature is falling at a rate of approximately negative, or sorry, we don't need the negative anymore. It's falling at a rate of 2.8 degrees Fahrenheit every week. And so that's an example using rate of change, both average and instantaneous, on a trig function. This is really no different than average and instantaneous rate of change from before. So if you're feeling okay with that stuff from before, you should be okay with this. And if you still have any questions, don't hesitate to ask. Hope you're all having a good day. You'll get the assignment at the beginning of next week, so on May 4th, and it won't be due until the 16th. So you have almost 2 weeks to complete it. I just figured I'd get it to you as early as possible and give you that flexibility to do it when you'd wish, and maybe you get it out of the way so you have no work the following week. All right, have a good day and goodbye.